Yeah.
So So because I missed it in the morning, so I'll go through with the lecture. So this is the last one. Okay. Kerry will come later. Just to get to know you guys. So you might have seen Kerry. So she will be taking over the module from me. Once today's lecture is done, lectures are done, and you will be submitting your assignment in a couple of weeks. Yeah. So she will mark it. She'll be involved in the marking. Yes. So, but I'll brief her on you guys as well, and how you are working and so on. So you need not to worry. Okay. So it's no, it will be a swift changeover. Don't worry. Okay. So yeah. So finally, we would like to talk about the errors in CFD. We will talk about the sources of errors, good practice, and summary. And I'll show you last year's paper as well towards the end. Most engineering flow problems are turbulent. So therefore, turbulence modeling is essential, and this is where errors large errors can come actually. So when you use a turbulence model, you need to know what turbulence models you use and why different turbulence models are important. So for example, if it is a fairly straightforward problem mostly in one dimension or two dimensions, or if it doesn't have swirl and so on, you better to use K-epsilon model because it's simple enough and it's robust enough. But if you're worried about the boundary layer and flow separation, etc., it's not good. So if you are worried about the boundary layer, you need to go for K omega or better SSD turbulence model. And DNS is the best. But with DNS, the problem is, what is the problem with DNS?
It takes way too long to calculate.
Yeah, it takes way too long to calculate. Yes. So and RANS also is good, but it is also slightly expensive. LES, large N simulation, is good for most of the calculations because it gives you fairly good accurate answers. Again, it's more expensive, computationally more expensive than the models like K-epsilon model and K-omega model. And so RANS-based models will be kind of the name of the game these days. And then we'll talk about errors. So what you're doing is making an approximate solution. So you're not solving anything theoretically, but you get an approximate solution. So the error is the difference between your approximate solution and the exact solution. So it depends. The errors always depend on your assumption. So you make an assumption. So if your assumption is wrong, your answer will be wrong. One source of errors is we use a grid, a discrete grid. So if your grid is not good, that will lead to errors. And turbulence cannot be represented properly. That will lead to errors. And then the other errors are because of your wrong assumptions or wrong theory. So if you go further into these errors, there are numerical errors. So that is the numerical, that is the difference between the exact solution of the partial differential equation and numerical solution of the finite difference equation. And then convergence errors, that is convergence between fully converged solution and the solution that you have taken. And round off error is the error that is due to the number of digits in a number of decimal places in a number. And then user error, so you can make the wrong assumption, wrong boundary conditions, something wrong by the user will lead to errors. And before that, there could be another source of error, coding error, meaning the person who has written the code might have done a mistake. So these are the sources of errors. How do we eliminate errors, or how do we get a better solution? One is when running a code, always use the default parameters as the first step. So just use the default. If you don't know anything, just use the defaults. That will give you a reasonable answer normally. Then look at convergence first, and so change some parameters to get better convergence. Okay. And then if it doesn't converge, switch to unsteady mode. So if your steady mode solution doesn't converge, switch to unsteady mode and run for some time, get an answer, and then you can use start as a starting point for the steady solution. Again, so those are like tricks that you can do. So for example, if you have a very complex problem with reaction and so on, always don't start with reaction straight away. Okay? Get a non-reactive flow running first. Get a flow field. Then once you've got the flow field, then apply reaction or apply complexity into the flow. Right? So always when you simulate, go step by step. Okay? So do the simple things first. So get a solution, and then use that solution as the initial conditions for the next run. Okay. So when you look at the residuals, now don't be too ambitious in the first place. So I know you're. So for example, velocity residuals, etc., you want to get to the 10 to the minus 5, but don't try it first. Okay, so relax it a little bit. Your residual size of the residual, relax it a little bit, and then do a test of convergence and different codes write the different residuals differently. So whether it can be RMS residuals or it can be the actual residual itself. When you have a flow problem, inlet and outlet, do a mass flow check. Okay? Mass flow at the inlet should be equal to mass flow at the outlet. Otherwise, there should be a problem. And you know that if they can diverge, the solutions always can diverge. And if it is an unsteady problem, or even reduce the time step. If you reduce the time step, the divergence, it will diverge less. Okay. And you can do something else as well. So you can find out the area where the maximum residual appears, and sometimes it may be only one point where you have the large residuals. So pinpoint that place and change the grid. Again, numerical schemes, when you use the numerical schemes, use more robust one rather than the more accurate ones first. Get a solution and use that initial solution as your final, as your starting point. So if you want to minimize round off error, so use double precision compared to single precision. But double precision is always more expensive numerically, computationally. And when you use grids, a body-fitted grid is the better one. But in a body-fitted grid, you should know whether you want to use a structured grid or unstructured grids. Well, structured grids, with structured grids you get better convergence. Okay. With unstructured grids you can have convergence problems, but with unstructured grids you can have smaller grid cells and penetrate everywhere in the body. So with complex bodies, unstructured grids are easier to deal with. So then you can have what are called block structured grids and chimera grids and hybrid grids. So now even in our problem, in this one you can have like two areas where you have two types of grids if you wanted to. And for example, if you have a complex area, you can use in a hybrid grid you can use text in the complex area and hexes in the other area. So you can have a structured and unstructured hybrid grid. So when you look at grid density, make sure that you don't go really coarse or really fine. Really fine means your computation time will be too large. Really coarse means your answers will not be accurate. Grid quality always it depends on the cell shape, aspect ratio, skewness, Pratt angle, etc. So don't have really skewed grid cells. You will get a rubbish answer most of the time, unless you have a unidirectional flow. So for a pipe flow, it is okay to have a skewed grid cell because their flow is only in one direction. So you need to have an understanding of the flow field when you do the grid. And also don't be too greedy in a sense, like don't try to use a very, very fine grid and get a good answer. So that's not the way to do it. Okay. So you might get a quite good enough answer even with medium grid. Okay. So make sure your grid topology for the problem is correct. So ensure the computational domain is big enough. So for example, if you have a very small domain, sometimes you don't really have to go really fine with the grid, because unless you are doing a DNS, you don't have to go really, really fine. So it always, and on the other hand, if you are if you are modeling, say, a building or atmospheric flow, you can't go small in grids. So your grid may be about 1 meter by 1 meter sometimes when you do atmospheric flows. Okay. So only you can have a very small, very high resolution, very small grid cells at the boundary layers, but not in the other areas. When you use an expansion ratio for grids, use something like 1:1, between 1.1 and 1.2. Don't go beyond 1.2 to be too skewed perhaps. And don't have too warped or twisted cells. So make sure that your grids are at the boundaries, your grid cells are fairly orthogonal. So don't use TETs near the boundary layer. Use prismatic cohexahedral elements. You have to avoid the high aspect ratio with the cell. Don't have large stretching ratios or expansion ratios between adjacent cells. You can do mesh adaptation, but mesh adaptation may not improve the grid quality. And again, use a very fine grid in the critical areas. You can do a grid dependency study, and when you do a grid dependency study, initially make sure what you are doing. Know what you are doing before you do this, because by using your experience, you don't really need to do a very large grid dependency study. Okay? You should know what grids are better for what conditions. This comes with experience. And boundary conditions, there are two types of boundary conditions, Dirichlet conditions and Newman conditions. So in Dirichlet conditions, you give the physical quantity. In Newman conditions, you give the first derivative. So, for example, dy by dx is a derivative form. So, if you don't use the proper boundary conditions, you will have problems. CFD codes. Some codes don't allow fluid coming from outside. So mass conservation is there. And don't have open boundary conditions sometimes. So I know you have a kind of a, in your problem you give a pressure boundary at the top. That's okay, but if you can avoid it, it's better. Okay. And when you use turbulence modeling, you know the models, eddy viscosity models, Reynolds stress models, and non-linear eddy viscosity models. So eddy viscosity models are quite robust. Okay, they are the most widely used ones. Yeah. So available models are Bolden and Lomax, Spelart-Almora model, K epsilon model, K omega, SST and Reynolds stress models. So, I can here. Have a seat. No, just have a seat. Yeah. I came late today, so I'm doing the lecture now. So when you use turbulence models, there is no universally valid model. So you need to use a model depending on your experience and the problem in concern. If possible, if you have time, you need to do a turbulence effect of or sensitivity of the turbulence model to the solution as well. A good way, I mean, there are a lot of there are a lot of literature around CFD and all the models that you are using as well. So you need to read. First, start with the guidance in the software itself, and then read a few papers as well, or books nowadays as well on what you are doing. So when you go to the industry, you will encounter a problem, but that problem might have been solved by somebody else, or a similar problem might have been solved. Therefore, always read. Do a bit of reading. Now, in this exercise also, what I am asking you to do is to do a lot of reading before you come up with a solution, or at least compare your solution with somebody else's work. So that is how you learn. That is how you accumulate knowledge. And for near wall conditions, use an accurate near wall model. Or an appropriate near wall model. Make sure you do that. And we talked about wall functions the other day. Use proper wall functions for boundary layer problems. And check the resolution of the boundary layer. Okay. So rule of thumb is at least use like 10 grid nodes in the boundary layer. And wall roughness has to be considered properly. Okay, so usually what you use is you say it's a smooth wall, but if the wall is actually rough, you need to say that it's rough. Yes, so it always depends. So if the problem is a low Reynolds number problem, so make sure your Y plus is for the first point is quite adjacent to the wall, and make sure you have 5 to 10 points between wall and Y plus is around 20. Yes. So the errors at the end is lack of attention to detail, too optimistic and uncritical use of CFD, lack of experience, unfamiliarity with the code, and now out of this, so the first two depends on the user itself, right? So these are the errors that you can have. So before you use CFD, train yourself. I mean, it's a good if you are going to work as a CFD engineer, and if you are going to use a code, don't be too cocky. Just go and do some training with the vendor. For example, if you are going to use ANSYS, I mean, even us, we go and train at ANSYS from time to time because they release the codes every year and so on. So we don't know everything, so we go and train ourselves also. So
do you know what error code 25 is?
Exit 2.
That exit non-zero exit code 25.
it must be a numerical. Non-zero exit means you need to change your boundary conditions.
Okay.
Subscribe to the same
Right. So. So, as I said, training is important, always important to do a good job. Okay, so this is where we are going to start. Do the start basically. So, how to do a CFD problem? Set up the problem. Set the levels of convergence. Analyze and look for errors. Do a grid independent study, and represent the simulation results. Okay, and some final remarks. CFD is not everything for the engineer, but it's a good part. To become a good CFD engineer, well, you need a lot of training, basically. This class won't make you a CFD engineer. You know how to use it. You will know how to use it. Yeah, but you need a little bit more training. So to become an expert, you need 3 to 5 years, perhaps. It's a lifelong process as well. So I mean, all 3 of us have I've been using CFD for more than 20 years. Yeah, but you have been using it. Yeah, I know you are much younger than me, Kerry. Yeah, 10, 12 years. David, 15, 20 years. Yeah. So, but we still get stuck with problems sometimes. Yeah. So experience is necessary. So these questions, ask yourself how to define the domain, how to judge mesh quality, what is the fluid model that you want to use, and boundary conditions. Now, all these, when you start a CFD problem, don't try to do it here first. Get pen and paper, draw it, write the boundary conditions, and think about it first. Yeah. So nowadays you may not use your pen and paper, you may use your iPad, but still draw it yourself first, and ask all these questions. And you need to know the limitations of the codes and the computers as well. Yes, so you can do a back of the envelope calculation for the size of the problem. Now, if you have like 5 million grid nodes, and will it fit your computer? So that's a very simple problem. So start small. Okay. Right. So that basically finish out benchmarking. Benchmarking is a validation and certification and benchmarking. Benchmarking means now there are benchmark problems for codes as well as your problems. So if you have written a CFD code, for example, there are certain problems that you solve with the code, and you should get these answers. So that is called benchmarking. So if it is accurate, you should get those answers. On the other hand, there are certain problems that you can solve, and those problems have been solved by somebody else. So you benchmark your results with those already available results. So that those databases are there. One good source is place is Sandia National Laboratory. So they have done a lot of fluid flow problems. They have a lot of data, lot of results on different types of flows. And CFD Online is a very good resource. CFD Online, because it's a user developed portal. But if something is wrong, people will say it's wrong and it will be removed. So it's quite a reliable source, CFD Online. Okay, so that brings an end to the lecture.